Welcome to this week's HAI seminar. Thank you so much for joining us. My name is Shivani. I'm a graduate student at Stanford, and it's my pleasure to introduce today's speaker, Professor Monroe Kennedy III. Professor Kennedy is an assistant professor in the Mechanical Engineering Department at Stanford University. He directs the Assistive Robotics and Manipulation Laboratory, otherwise called the ARM Lab, which develops collaborative robots. He received his PhD in mechanical engineering and applied mechanics and a master's in robotics from the University of Pennsylvania, where he was a recipient of both the NSF and GEM graduate research fellowships. As I mentioned, his area of expertise is in robotics, specifically in developing theoretical and experimental approaches to perform modeling, control, and estimation for robotic systems, with applications that include manipulation and human-robot collaboration. What excites me about this research is that it is about robots, but always for people. And there seem to be no limits to the areas from which it can draw inspiration and to which it can contribute. I'm fortunate to be advised by Professor Kennedy at the ARM Lab, and I'm looking forward to moderating today's session. Please feel free to use Slido to submit questions to the speaker at any time during the seminar. There's a QR code on the screen, and there will be a link in the chat as well. After the talk, I'll do my best to bring up as many of these questions as possible for discussion. And I will now hand over to Professor Kennedy.
Thank you very much, Shivani, for that amazing introduction. So I'm happy to be here today to talk to you all about considerations for collaborative robotics. So I run the Assistive Robotics and Manipulation Lab, and our goal is to develop intelligent assistive technology that improves human life. To accomplish this, our research sits in three main areas: robotic assistance, intelligent wearables, and connected devices. And later in the talk, I'll give you some examples of existing projects in all of these areas. We really look at this interplay between a robot, human collaborators, and a complex task or environment in which the robot and human have to operate. And we propose that to be an effective collaborator, teammate, assistant, the robot has to be able to model itself very well, the task, as well as the human collaborator. I'm very fortunate to have found many amazing students in the year and a half that the lab has been running, and you'll get to see all of their highlighted work later in the talk. So getting started, let's think about the path of robotics that has led us here to collaborative robotics. In the 80s to the 2000s, you really thought of robotics in the space of automation, robots that would be able to complete a repetitive task well and precisely. And then on the turn of the century, we really saw the emergence of autonomy, robots that had to perform well in unstructured environments. We saw interest rise in swarm technology, which consisted of both centralized swarms and decentralized swarms, which we'll talk more about in a moment, where robots had to team together and were either told what to do from a single oracle, or they had to make their own decisions and reach consensus. And now we see the onset and need for robots that can actually work with human teammates. So to kind of calibrate ourselves to what kind of tasks could benefit from having human-robot collaboration, some of these might look like cooperative carrying. You can imagine having wearables that can help someone walk or detect when fall might be imminent. You could have robots that could help in moving objects or completing a complex task. You could have wearable robots that are intelligent and can perceive the environment and extend the abilities of the human that's using it. You could imagine thinking of robotics in the case of autonomous vehicles, particularly how can the car and human work together? And even more passive robots that may not necessarily have actuation, how can they enhance abilities such as serving as interpreters? So today I want to ask three main questions. One is, what makes an effective collaborator? What tools do we have and what do we need to make robots effective collaborators? And finally, what must be considered for human-robot teams? So starting off with what makes an effective collaborator, if you think about how robots usually work together, or how they've worked together for many years now, what might come to mind is having some sort of centralized or decentralized control with some digital communication. These robots are able to talk to each other, and through that, if they have an agreed goal, they're able to operate in unison. As the scale of these robots increase, sometimes this can actually overload a centralized system that's supposed to compute and talk to all of the agents. And as the distance between the agents increases, it becomes more and more important that local decisions be made and shared among neighboring agents. And so the key in these sort of systems is that the system actually reach consensus on what that desired behavior is and understand their particular role. If we begin to look at nature for inspiration, we see that biological agents are able to do incredible things without digital communication. And so when we watch these amazing feats of nature, we have to ask, what makes an effective team? I argue it consists of having shared goals and objectives between teammates, the ability to model other teammates' behavior for prediction, and finally, the ability to plan given your personal and teammates' roles in order to accomplish the objective. So when nature, biological agents perform these sort of amazing tasks, we have to think about what are their communications modalities. And often it comes down to audio, vision, or tactile. So audio is great. We're using it right now. It allows for high specificity, but it can be very slow. And if you have a very fast operation, it may not be able to keep up. And it's also subject to sequential speaking and listening roles often. Vision is a little bit better because we can mutually observe each other, and information exchange can be extremely fast and very detailed. Here, these dogs are looking at each other and they're able to know where each of them should be in order to cage the geese as they walk. You can also imagine in the space of vision where a single agent may demonstrate a complex plan to others visually, as you're familiar with honeybees being able to communicate a path to food to other agents at the nest. And finally, tactile information, touch forces, can be very fast, but you have a proximity requirement. So here, the game is being communicated via tactile response, but clearly you have to be close enough to touch the person. So key features of this sort of teamwork are A, understanding your role. So given the actions of others, what is my role? And is my role unique given the task? And this notion of interagent trust, which is going to be very important throughout the talk, and really set stones this notion of collaboration. And we define it as A, having an agreed objective, and B, having a known behavioral model. And we separate these because you might have one and not the other. So let's consider this lane changing task where red is trying to decide if it's safe to switch into the lane where blue is. In order to trust blue, the objective must be agreed upon. Blue must also not want to collide. And the behavioral model must be known or approximated. Blue will maintain a particular velocity in order to achieve the objective of not colliding. If these two things are true, then this can be the basis for red trusting blue in taking that lane changing action. And in busy cities, this is a very important feature that allows you to merge in very tight traffic. So what are the limitations of biological agents? You have limited communication modality, limited dexterity and strength to weight, and limited perception. But biology overcomes this by understanding the role given the team or task, modeling the task itself, and also modeling other teammates as well. So let's shift to begin thinking about what tools we have in robotics that can make effective collaborators. I'm going to touch on three main areas, but this is not exhaustive, but particularly in the space of manipulation, these are very important. Proprioception and control, knowing where you are and how to control yourself internally as the robot, the ability to perceive your environment, and then having some intelligence so that you can model and make decisions based on what you observe. If we quickly cover the sort of proprioception and control space, particularly a lot of robots have internal sensors that allow them to measure where, for instance, components of their body might be. Here you can see an example of forward kinematics and DH parameters. And perhaps the internal dynamics model is even exposed to the robot. It knows how its motion will be governed when there is acceleration applied into the system. We have motion planning that we can perform based on knowledge of the kinematics and dynamics. Here you see a sample-based method, possibly planning the different motions of a redundant manipulator. And then we have control, right? How do you actually interact with your environment if you're touching it, or if you need to essentially exhibit some dynamics? What control input will allow you to exhibit the dynamics you want to see? So expanding a little bit on the control phrase, and again, focusing more on instances of contact. Depending on how you want to interact with your environment, one common modality, particularly for touch, is the use of either impedance or admittance control. In the case of impedance control, there's some sort of mass that you want the system to mimic. You want it to have a particular stiffness when it interacts with the environment, which gives it a virtual mass, if you will, dampening and springy force when interacting with the environment. Admittance control is exactly the opposite, right? You want to have this sort of passivity to your environment in order to accommodate this. And this is useful both for, manipulation tasks, for walking robots, any case where you'd actually want to touch your environment. In the space of perception, right, we have camera sensing, which has just grown leaps and bounds over the years. Here you see the ability to detect objects of interest. We have laser-based rangefinders that actually send out signals to their environment and measure the time it takes to come back to give them good measurements of the environment. And finally, we have touch sensors, tactile sensors. So the question we can ask ourselves is, particularly thinking about, possibly what is keeping robots out of people's homes, I would argue it's the ability for them to safely manipulate objects in their space. And so really developing tactile sensors, I think, is a very high priority in the robotics community if we want to see robots exist independently, autonomously, and with a lot of capabilities in someone's home. So this is where we want to be, right? Look at this amazing video by OpenAI, where you're actually solving a Rubik's Cube in one hand. This is achieved right now through cameras that are externally observing the system, multiple cameras observing the hand, and extensive training in RL to figure out what works and what doesn't work from this type of observation. If we want to have an approach that allows us to have some knowledge of the frictional and contact information, this is where we are. So this is GelSight, an amazing sensor coming out of MIT, and now a company is involved with this. And what you see on the top corner is cameras looking inside of the sensor and able to measure the normal and shear forces as it puts the ball on the peg. So if we look at the space of tactile sensors, right, we have the traditional 1D piezoelectric mechanical type of tactile sensors. We see the onset of using vision-based sensors that are highly dexterous because they give you a lot of resolution at the point of contact, but some of the early ones were in fact 2D. This improved, and here you see this pneumatic gripper to 2.5D, so it's kind of curved, but it's still hard to manipulate things, especially soft objects and curved objects with these 2 and 2.5D sensors. And then finally, we see the very recent emergence of 3D shaped vision sensors. And this has been an objective in our lab as well. We're interested in also developing these tactile sensors, which will enable robots that are intelligent and able to operate with people in their environments. And we see this problem as having 3 main phases. We need to design a sensor that's anthropomorphically inspired, curved, and able to manipulate objects and sense both normal and friction forces. We want to leverage the history that comes with contact modeling and mechanical engineering from the last few decades with some of the newer tools we have in modeling these high resolution surfaces in order to better inform our motion planning, which would then bound the search space and training so that we can actually manipulate very complex objects with high resolution knowledge with guarantees for safety and stability as we're manipulating these objects. So here my student Wankyum has developed a first generation of the sensor that uses a fisheye lens to observe the boundary of the interior of the contact surface. So the gel itself is translucent except for the boundary, which you can then observe with the fisheye lens. And so this gives you an idea for scale. And essentially when there's contact on the surface, right, it actually deforms the surface, and the LEDs that give us multiple snapshots as it rotates on the circle essentially gives us knowledge about the depression of the surface using the shadowing that you see on the Lambertian surface. So our goal is to calibrate such a system and actually correlate the vision that we see, the image, to the expected deformation of the surface, as well as the expected forces, normal and shear, at the surface as well. And as we complete this, right, our goal is to actually use models, particularly generative stochastic models, to model that smooth, continuous surface, to get that normal and friction forces and have a notion of uncertainty, so that when we grasp them, we can actually build wrench cones, which essentially tell us how we can manipulate an object before it slips out of our hand. And if we have these high dimensional surfaces, motion cones for our system, then we can actually use these in our motion planning for in-hand manipulation. And so here, this is some great motivation from Alberto Rodriguez lab at MIT, where they did planar in-hand motion for motion cones, where they pushed objects against surfaces. For us, the goal would then be to have wrench cones for in-hand manipulation that are informed by these high dimensional surfaces. So now shifting to another attribute for robotics is intelligence. Right? If we look at the taxonomy, particularly for intelligence when it comes to predicting your teammate, we'll call that trajectory forecasting. You can break it down in this very nice taxonomy that comes out of Marco Pavone's group here at Stanford. And what you see is you have these sort of theories that assume there's some core underlying structure, which may or may not be true. And then some phenomenological methods as well, so data-driven methods. And particularly if you're trying to predict the behavior of other agents, you have to realize that usually there's some stochasticity that could come from just the randomness of someone making a decision localized around a particular goal, and then also their inability possibly to execute exactly what they're thinking. And so generative approaches, these stochastic models, help us with that type of prediction. And so if we think about, again, the tools that exist in robotics already, we have these notions of consensus and swarm behavior, right? And so here I present both a centralized system and a decentralized system where the agents actually work together. They might have an oracle that tells them all what to do, or they perform information averaging through consensus or voting in order to determine what their actions are. But most of these implementations are conditioned on the availability of digital communication. So what must be considered for human-robot teams? So I would say a key challenge for human-robot teams is that the digital communication is unavailable. So what do robots need to be effective teammates for humans? They need the ability to model complex tasks. We need the ability to interpret and manipulate environments that are originally configured for humans. And we need the ability to model teammates' actions and roles. So given these three primary objectives which drive all of this, I'm going to begin addressing some of these within some context of problems that we're actually performing in the ARM lab. But this is a critical point, a critical position where I think if you have systems that can do all of these, this is what it takes to actually have good coordination for human-robot teams. So one way I'd like to break this down is with this sort of taxonomy, wearables versus external collaborators. And so on the wearable sides, this is human augmentation. It could be ability substituting devices or ability enhancing devices. And then external collaborators are those that are outside of the person and serve as sort of a partner. So for the wearable case, let's first think about ability substituting devices. Here you have the human and a control loop that kind of shows you what the human has to do to interact with their environment. There's cognition, how do you plan and control? There's body dynamics, which serve as your plant. And then there's sensory feedback that allows and informs future planning and future control. And so if you have some robotic system that's augmenting, the questions you have to ask is the robotic augmentation functionally adequate? And does the presence of the robot feel natural or easy to use? So I'd like to showcase this ongoing work being performed by Shivani and Gabby in the ARM lab. We call it the intelligent prosthetic arm. And so we really focus on cases where people have had full shoulder disarticulation, but it's useful to even think about other cases where the amputation has happened lower down the arm as well. But we think that thinking about the shoulder will help us have a more complete vision of the end product that we'd like to see. And it's really hard for these existing solutions to provide people with the kind of dexterity they may have had before they underwent that amputation. And that's our goal, right? We want it to be easy to use and provide a lot of dexterity in the end. So the challenge is here, right? Again, we can phrase this in our robot, task, and human paradigm. The trouble is, how do you actually specifically extract the human's intent from the system? And this is very difficult, especially when you want to remain outside of the person, possibly like with surface EMGs. How do you actually achieve this? We realize that mixed reality can play a really big role, because if we can have someone wear such a headset that they can see the environment, but virtual things can be displayed, and if the system has eye tracking, then you can detect what the person is looking at and even display things in their environment that will help you query and understand and ascertain their true intent. And so between EMG measurements and mixed reality, we think we have a really good shot at making a very capable system. So to kind of set stone this, if you think about an able-bodied person, you have this sort of, again, this sort of control diagram, the cognition, the plant, and the sensory feedback. And what's great is, as robots have developed today, we actually have the ability to mimic each one of these spaces, the cognition, the plant, as well as the sensory feedback. So an able-bodied person, right, every aspect here works well. In a powered prosthesis, usually EMG or the like are used to control it. So you send an EMG signal, this fires the actuators and changes the body dynamics. Some devices might have some low-level reflexes that are based on some really simple feedback modalities. You can think of, let's say you were touching something hot, you can have an immediate response that just withdraws the prosthetic from something that's hot. And then we have the design we really would like to achieve, which is an intelligent power prosthesis. It's able to observe what the person is looking at, ask them questions, be a part of the planning, as well as take direct control inputs and feedback from the environment. So we briefly mentioned augmented reality, and it's a very powerful tool that will allow us to both extract and present information to the wearer. And so you can think of gaze tracking as being a conic section based on where the person is looking as you go out in space further from the person, and you can leverage advances in machine learning and computer vision to actually recognize objects in the person's space. So an example of how such a system could be used is thinking about, for instance, a particular activity of daily living, like feeding yourself and drinking some water. So this can be thought of as a state machine if the robot were to do it itself. Here, the purple lines are the trajectories that the arm might follow, and the circle with the cross inside is the focus for the person's gaze. And so based on what you're looking at, you might realize that the person wants to, for instance, pour water first. And then because there's not a lot for the pitcher to do, maybe you only need an EMG signal, for instance, to indicate that you want to pour into the cup. And then after you've completed this task, the options that might remain are feeding yourself or looking at the cup. And if your gaze is focused on the food, that might raise the probability that you actually want to feed yourself. And so you can complete that task and continue feeding yourself, where maybe looking at the food, the arm can figure out where it should attack next in order to help you enjoy your meal. So this is the intuitive understanding of what we see this being at the end of the day. But let's dig a little bit deeper into how we might actually phrase this mathematically. So if I think about a few variables, like the state of the system, which can include the arm and the environment, we'll call that S, the gaze from the person, G, the EMG signals, E, and the desired action, which could be continuous, A sub I, then what we've really done here is we want to think about what action does the person want to take given the information about the environment and inputs from the person. So when you think about how an object might be used, we typically call this object affordance. And so we're thinking about what actions would you take given the way these objects are usually used, what their affordance is, and the EMG and gaze input from the person. To find that value, we argue that it's important to model the human's behavior. How would you fire the EMGs and look given a particular state in action? If we told you do this action given this state, what would you do? We need to understand that. And then we need to understand the context of the task we're asking the person to complete. What action makes sense given the state of the system? What's the affordance? If we find all of these, we can kind of think of this in a Bayesian network sort of paradigm where we can actually use these different quantities to solve for what action the human wants to do, given all of these inputs, both for the person and the state of the environment. And so highlighted in green are behavioral model components, and then highlighted in blue here is the intent model. And to predict what action the person would want to take is taking the argmax over this probability distribution. So let's again play this out and see what this looks like to ground our intent, our intuition. So here you can imagine the arm performing object recognition. It sees that the things to interact with are a cup and a pitcher. And so now we have task understanding. If the cup is empty, there's a higher probability you're going to want to pour from the pitcher first. And then you want to verify with the person, what are they looking at? What are they interested in? You could use that gaze tracking to determine where they're focusing on the table, and that can inform what object they want to manipulate first. And as you begin to reach, the arm can actually, the EMG signal you can see firing there on the lowest could be used to actually drive the expectation of where you want to reach as well. And so if you superimpose these probabilities, all of these can work together to inform the arm what the underlying intent for the human actually is, based on the context of the problem you're trying to complete. And once you have that knowledge, then you can execute with a high probability of doing what the human actually intended. And so practical considerations for implementation, again, there are quite a few ways to do this, from Bayesian networks straight up. But one way we are interested in doing this is a stochastic generative model here, conditional variational autoencoder. And so I present this just showing how you can actually encode the expected task, Y, the action, given your input X into a latent space, which correlates to the strategy of the person. And once you validate or understand the different strategies that the person is trying to execute, then you can use that information to help you correctly understand their underlying intent and be an effective collaborator in manipulation. And so what we want to do is set stone this for both understanding the action given the state of the system, as well as the inputs from the human, E and G, given the state of the system and a particular action that's requested. So what's fantastic about this, right, is, we realize in this sort of breaking up in this sort of Bayes paradigm, this means that we can train and test everyday settings, even with non-amputee subjects. So here you can imagine having a person complete these tasks of everyday living, sending them up to a cloud, and then someone who actually needs to use these for a prosthetic could benefit from those experiences. And on the other side too, traditionally what's already done, calibration is very critical currently. And so you can imagine using one of those calibration setups, which will allow you to adapt more specifically to an individual's needs, and then leverage from the person, from the community, all of the different tasks that they want when you combine these together. So right now in our lab, especially kind of informed by our pandemic restrictions, we realized a really great way to test this would be to actually put everything for the moment in augmented reality, including a prosthetic arm that's attached to a person, and have the person complete virtual checkers with a virtual opponent. And so in doing so, we can take the rules of the game to inform us of what is the action, what is the affordance, what is the probability of taking an action given the state of the system, and then have the gaze coming from our HoloLens system and having EMG inputs as well to help us understand what the person wants to do, and then use this to validate our approach and understanding if we can actually perform this well. So this is what we're currently doing, but as soon as possible, we plan to build our collaboration structure here and then think about how we can actually move to eventually using real prosthetics and helping people with this necessity as soon as possible, and applying this to activities of daily living. And so the end result here would be fantastic if we could basically think about existing prosthetics, their max task performance, right? What kind of dexterity do they have? Can we raise that higher, right? What you see here, raise that higher, and shrink the learning curve so they're able to reach that maximum capacity of their arm sooner. So next I'm going to move to ability enhancing devices. So an ability enhancing device usually improves sensory feedback concerning the world. And so this is saying the person might be able-bodied, but whatever ability you had before, how can it augment it or make it better? The first project I'd like to discuss in this space is really fall prediction and prevention. So here, we know that falls are the leading cause of fatal and non-fatal injuries in older adults. But if they can be predicted and mitigated with a wearable sensor, could this actually reduce those falls in that population? And so our objective is to have a wearable sensor that's able to perform visual inertial odometry, understand where you've walked, see the environment, predict your path in that environment, predict your gait in that environment, given your past gait, and then have a vector that measures the orientation of the person and the variance of that vector. And it's been shown that balance is correlated to the variance of the sway of the individual. So if you can predict that the sway is going to increase, that can be correlated to the possibility of the person falling. And so if you could have a vibrotactile response on the person that indicates to them on a longer horizon, think on the order of seconds, then you can alert the person that they need to become more vigilant. And that might also, therefore, reduce the risk of them falling as they continue to walk. And we want the system to sort of be lightweight. It should be able to sit on the person's torso, extract the necessary information, and predict all of these things. This is a demonstrated architecture you see on the bottom left that we're thinking of using the history of inputs from the person to predict those future parameters, which is necessary for the fall prediction. And what's great is, while we have this immediate sort of customer in thinking about fall prevention, this can absolutely be extended to lower limb exoskeletons and helping them to plan on longer horizons, or when the person is actually moving faster and there's not a lot of time to intercept signals from the person's brain to the system, given the dynamics of the walking. Another idea for an ability enhancing device is an interpreter, right? So, we want to bring together communities, and one is helping non-ASL speakers to communicate better with ASL speakers, very similar to the way Google Translate works. We're not the first to have this idea, but we have some ideas on how we might actually improve this for mobile computing. And one way to do that is to do sort of a modular network. So how can we first think about key features that are necessary to extract information, and then once we have that, feed that into a transformer, which allows us to predict the ASL to English text, which could then be spoken if desired. And so our video actually has improved greatly in the torso tracking, and this is very promising. So moving now to the space of an external collaborator. The first example I would like to give is a project in collaboration with the Iliad Group, Dorset Sadiq's group, on having a human robot team for cooperative transport. And so going back to that notion of interagent trust we talked about before, it's important that the agents be able to understand what their mutual objective is and what each other's execution strategy is. And so to achieve that, we believe we can observe humans carrying objects together, learn those latent strategies, and then allow a robot to execute that through imitation learning and improve on that with reinforcement learning. So again, due to challenges of COVID, our very first attempt at attacking this is actually using simulation, which in itself actually brought out some really nice abilities for us to test. And so by using humans that first work together in simulation, we can understand how the humans' policy would work. What actions would they take given the state of the system and possibly surrounding obstacles in the environment? And then we can use that sort of imitation learning to train an RL agent that is conditioned on the latent strategy of the human participant. And what's great is when we do this, what we hope to do is kind of perform a Turing test in this environment where the one of the humans tries to predict whether they're working with another human to perform this task, or in fact a robotic agent. And then in the real world, we plan to do this again in case there's any variations between the simulation to real, and then see how the human collaborator works with a robotic agent. And this project with Aaliyah and Manuel, the goals here are twofold. One is to increase the efficiency of learning from demonstration, and doing so through essentially telling the robot what features are really important in order to complete the task. and then having the robot have the ability to perform active learning, where based on that description, the robot asks the human different scenarios that would improve its understanding of the environment, and doing that using the latest tools, machine learning. And then once you know a task, if there's a collaboration where you want the robot to work alongside the human, can the robot actually predict the human's actions and understand what it should do in order to make the overall team more efficient? So let's say you're carrying a group of heavy and light boxes. The boxes were too heavy for the person, but maybe the human has a suboptimal strategy where they carry heavier boxes. By observing the human over time, the robot can realize that it's the most efficient thing it can do for the team is carry the heavier boxes, which would force the human to carry the lighter boxes, increase, therefore, the overall team efficiency. In this project for leveraging human intent for shared autonomy, I have it listed under external robot collaborator, but it could also be considered perhaps a wearable, but because the human is interacting with the environment through the car. But the idea here is, sometimes you may not want to actually just have the car drive by itself. Maybe you might want to have transition between the human and the autonomous vehicle. And if you want to transition at non-zero speeds, how do you make that safe and smooth? So again, coming back to this paradigm, we have our intelligent vehicle as the robot, literally the environment, and the driver as our human collaborator. And this has been motivated quite well, I think, in movies that you might want to take over at some point at a non-zero velocity. So how can you control and determine when you should take control and when control should be given back to the person, particularly when the driver asks for control when they don't necessarily, the car is not in danger of crashing, but the person would like to drive when the car is at non-zero speeds. So if you think about the levels of autonomy here, I believe levels 3 and 4, conditional automation and high automation, are very suited for this type of thinking. And so what are the risks for arbitrarily taking control from the human? Does the vehicle have an accurate model of the plant dynamics? And so if the vehicle can convey its plan to the human, right, then this can be a very useful condition for the robot to know if it's safe to give control to the vehicle. And then going the other way, what are the risks for giving control back to the human? Does the human have an accurate internal model of the plant dynamics and effective control strategy? So the question is, how can we actually determine this? And I believe the answer is through human intent estimation and action prediction. So consider this idea of the car turning over control to the person at some switching time TS. The question is the human strategy going to keep the car in the lane, which is the safe set? The vehicle has no idea, right? What is the human strategy? What will happen? However, if the car and the vehicle can actually give the human a sort of trial period, take their inputs, and then determine if that inputs that they're performing would remain in the safe set, then it can understand their latent strategy and blend control as it transitions with a high trust that the person will remain in the safe set. And so the kind of argument you could imagine setting up here would be having some sort of human action model, some state transition model, and robot action policy conditioned on the human's actions and the state of the environment in order to be successful. So takeaways I hope that you got from this section are: to be effective collaborators with humans, robots must be able to model human behavior and their role. There's significant room for improvement in robotic hardware for alternate forms of communication like audio, visual, and tactile. And robot collaborators have the potential to expand their human teammates' capabilities, enhancing and restoring their quality of life. Thank you very much.
Thank you, Professor Kennedy. We have a number of interesting questions here. I'll start with one of my own, which was when you were talking about the way that audio is sequential in conveying information, and vision, on the other hand, you can convey a lot of information simultaneously. Do you see a distinction there between the way that when you convey information through audio, it's usually also there's some form of representation involved on the way. So you have to put it into language first and then transmit it. Versus in vision, you could have a visual representation like the bee dance, but then you could also just have watching the thing happen that you're talking about is happening. And do you think that's an important distinction to make, or is it more important that, so is it like the representation versus the actual event, or is it, can you see everything at the same time versus do you have to do it sequentially?
I think that's a good question. And uh, I think there's not a really easy answer because if you think about the range of audio communication that we're aware of to date, right? Some languages are very efficient. People speak very fast and they can convey a lot of information well. And in some languages, it's traditional that the time between people speaking is actually very short. And so there's not one unified answer, I think, in the audio space. However, it still has that sort of sequential nature. And you're right, the person needs to take whatever high level idea they're doing and present it in some sort of sequential audio fashion to convey that. And depending on the complexity of the idea, it may be better, right? When you think about describing mathematics, it might be easier sometimes to speak in an audio way to give a higher, more complex idea in a very compact way. But when you think about the speed of an ongoing collaboration, right? If you go back to those, playing a game or, herding, right? The visual was really good because there was sort of this implicit notion that the communication, the things you needed to know were conditioned on, did you have the same objective? And did you understand the behavior of others? And that through observation, direct observation, was really easy to pick up and really fast. So yeah, I hope that answers that.
Thank you. I would actually think that even from that point of view, vision is easier to use just because then if you have a representation, you need to also teach your system to interpret whatever representation that is.
Yeah.
Uh, so related to that, there are two questions about the bees analogy in Slido. One is, can you compare the similarities and dissimilarities of your systems to a bee colony? What is the maximum number of robots you can handle within your system? And do you know the same number for bee colonies? And then there's a comment that bees and ants communicate also via biochemical agents, not only vision, which is a comment. But I'm adding a question to that. Is there a robotic analog to communication via biochemical agents?
Okay. So to the first question, uh, so uh, if I remember correctly, for the first part, it was if you have the bees walking around. Um, Sorry, can you repeat the first part?
Yeah, sure. Can you compare the similarities and dissimilarities of your system to a bee colony?
Yeah,
And what is the maximum number of robots you can
yeah,
handle?
yeah. So to that, right, it was a modality that I mentioned. I currently don't have an implementation that uses this, but sort of similar to this audio component, right? If you're observing a demonstration, right, like the bees are demonstrating a task to the other agents, they need to kind of wait until the dance is done in order for them to actually act on that information that they perceive visually. But maybe, for the bees, it may have been easier in that case to perform the action than try and communicate in some other fashion, like through the pheromones, where, for instance, the flowers are, right? And so I think in that regard, maybe doing some demonstration or action for the robot can signal to the person. I think this kind of goes to the signing idea, right? I would say the bees are doing a form of signing, right? So maybe this is actually how you're communicating, and I think that's a perfectly valid approach to do that. How does it scale? I think comparing that to, let's say, digital, if you don't have a lot of bandwidth, if you can observe the agent, then it scales to however many can actually be in a range to observe that action and pull information mutually from that system. So I think that, that visual component might scale particularly well. And I think any, robotics applications that leverage that, I think would be really cool and unique. To the second part, which is on the pheromone communication, absolutely, right? This, is how they might communicate. The question is how much information is actually encoded in that pheromone modality. I personally can't speak to that, but I would imagine that while it would, definitely be surprisingly high, as what we might think, uh, you know, uh, currently, I imagine it's definitely probably far less than what you could do with vision or some other method. But who knows, right? So, if you want to think of that in a signal space, right, I think the ability you have to A, produce and B, sense specific chemical signals, then that would be the basis vector, if you will, for that language. That's how I would begin to think about that. And so, yeah, without further knowledge of that, that's what my initial thoughts on that would be. As far as robots using those, to my knowledge, not a lot do. If you actually think about these sort of sensors that actually can use smelling, a lot of them are really geared toward very strong substances. Like I worked on one in graduate school that was able to sense the smell of, like, rubbing alcohol and tell you what the concentration was and give you concentration gradients as you moved the sensor. But I'm aware that it is an active area of research in physics to actually develop sensors that can actually sense or smell more complex instances. And as those fields co-develop, we could totally imagine having robots that have the sense of smell. And I think that's another very interesting avenue.
There's a question, would it be possible to have multiple robots collaborate with each other, not just with goals and roles, but with adaptive planning? So each robot is creating the best winning strategy and sharing it with each other to make the common best plan for success.
I think absolutely. And I think the notion of trust may still not go away, even in that scenario. So, if the policies are divergent or you're operating on information that, there's a disparity in the information about what all the agents possibly know, if you trust, these other agents that they're not acting in a suboptimal way, then if they're performing a behavior that's unexpected, right, then you might have a higher probability of taking action that will lead to consensus with that teammate if you trust the fact that they're geared towards some higher level objective. So again, I think back to possibly the cooperative carrying example. If you both agree on the goal you want to go to, you could have one agent sense an obstacle that the other doesn't see, and they apply a force, and you have to have some admittance because you know that they wouldn't apply a force for no reason. They're doing this possibly to meet some higher objective, like not colliding. However, if you have a nefarious agent, and that's a whole field of study, they may take actions that as a team, you might want to just, robust control, filter out. And so how do you determine if you need to filter out other agents or if you want to adapt their input that's unexpected? That needs to be conditioned on something. So if you can communicate these larger strategies in some way, like again, if we go back to the digital case, then absolutely, I think that's a very easy thing to do. But if that sharing isn't possible and you have to just observe through the actions of others, then I think trust is interagent trust is still a very critical component to that.
What are your thoughts on making these collaborative systems more robust towards model misspecifications? Specifically, this question is about the model of human behavior being misspecified.
Right. So that's a fantastic question. So, this kind of goes back to that taxonomy of how you might actually model the behaviors of others. I think if you kind of pigeonhole yourself into the ontological or deterministic, it might be very hard to adapt to uncertainty, in that human model. But beyond even uncertainty, which stochastic models help provide and can help accommodate, I think another underlying part of that question is, what if your strategy or your estimation of the strategy is just completely wrong? Right? The latent strategy of the person is just in a completely different area. Can your system even adapt to that? And I would say, I'm aware of some works that are actually beginning to ask that question, right? What does it mean to have a movable latent strategy, or one that can update as you interact with the person? If I go back to the example I gave for the human and the robot carrying a box, right? As you're working with the person, you're actually trying to identify what their strategy is based on previous work. But if you work with them long enough, you can actually build up some, notion or model of their strategy just through the observation of them, if you can work with them long enough. So, I think, if you can observe and work with them long enough, you might be able to ascertain what that is. But there's another part of that, which is, in time, they may also adapt to the robot or to the environment, or their goals may change. And so how do you handle just a moving target, I think, is a really open area of research.
As communication bandwidth and local computation ability both improve, how do you see the trade-off between centralization and decentralization evolving? Or perhaps more importantly, where will each approach dominate?
So I think if you imagine you have all of these quads on a 5G network and you have massive computing abilities, if you think about implementation, a centralized controller can be really good, right? If that communication is not a question. But I think there will always be scenarios where that's challenging. So if you imagine, going to a place where communication is just hard for a centralized system to execute. Let's say you had quad orders flying over the North Pole surveying this region and there's no 5G networks up there, right? They still need to be able to work, right? You want to be able to take your briefcase of quads and just have them work. So then in that case, agent to agent communication is extremely important. And if that can still be good, then if, let's say, the bandwidth between the robots is high, then this can inform consensus strategies really well. So if you can send more information faster, they can actually, ping each other faster, and they can reach consensus faster between their systems. So I think that's the kind of trade-off we have in those different spaces. And a lot of that, I think, is really application dependent.
There's a couple of ethical questions. There is one about the challenges with swarm weapon technologies falling into the wrong hands. And there's one that it says, are there ethical concerns with a robot rejecting a human who wanted to take control of their vehicle or other device? And should a robot have that kind of admin control?
Yeah. So I think the first question, which is, just the general ethics, right? How do you make sure your technology is not used for bad, is a really important question, and one that I think the community is working to answer even now. And I think some notions for that is, like, if you were to be an engineer designing a bridge, right? You're thinking about what kind of safety factors and features you can put in. So I think a huge component of that is in our design, but along with that, as your tools become more powerful, and this is not just in robotics, it's across all advances in science, the agents who use them can be just as creative as those who made it, right? And so I think there's a bigger social conversation that needs to happen on how do we make sure that as we make our tools just across the board, be it robotics, any science technology, how do we ensure that is used for only good and not bad? That's a social conversation, because those who would use it for bad or could use it for bad are just as smart as those who made it. So we need to have that bigger conversation that's even scoping out of that phase. For the vehicle that may choose not to give over control, I think, I again, going back to this notion of built-in safeties, right? I think you can definitely imagine in an end scenario having a switch where you're like, I don't care whether you trust me or not, this is mine now. And you can implement such a thing like that. But the question is, for instances of safety, maybe as the trust builds with the robot, you want it to be able to make those co-decisions with you, right? If you're driving on the highway and if you were to take over, it's confident that you would crash, and there's data to support the fact that it would be correct, then maybe I would not want to disable that, right? I don't disable, for instance, my anti-skid brakes that take over the braking mechanism when I begin to slip in my car. I grew up on the East Coast, and now the whole world is experiencing this. Thank goodness for the anti-braking systems in our car that can help, avoid slippage in some cases, right? I don't disable that, although there's a button that I can push to do that, because I trust the car to perform that operation and hopefully reduce the risk of me crashing. So can we build systems that people trust and are very effective, so that we can make the whole situation safer and more enjoyable?
Absolutely. Apart from the outcomes of a collaboration, what metrics do you think are important to assess how the humans feel about the collaboration?
So so operational success is important. I think also considerations, one good metric you could imagine is if this is something that the human would normally do by themselves, like imagine the prosthetic, or if this was something that the humans would do with other people, possibly if those kind of attributes are desired, which we usually associate with having some correlation to success or optimality of the task itself, but if they feel natural, right? I think these are other metrics that we can ask, and some of them are going to be qualitative metrics as well, but I think those are other things to consider.
Uh, so there's a scenario described in one of the questions. A person reaches word for a package on a table and another person tries to stop them from picking it up. But the first person still manages to wrest their arm from the other person's grasp and pick it up. A robot watching this, how can the robot be trained to understand that the second person's actions were not part of the accomplishment of the task, but it was actually an impediment?
So I think there's two parts here, right? So um, in the specific example I had given, right, the goal was to ascertain the intent of the wearer, right? So if the arm that was interacting were not the person's other arm controlling it, but some other person's arm, right? In the scope of the problem we currently have, where the intent that we're driving from is coming from the person, right? So what are their EMG signals? What do they care about? What are they trying to grasp? Right. And so then the question is, what is the control paradigm you use in the hand to accommodate any type of external disturbance? Is it an impedance controller? Is it an admittance controller? Right. And those are design considerations you need to have. Most likely, we would have some sort of admittance control strategy such that, you don't force your way through anything that shouldn't be, have, super large forces applied to it as you're performing a particular task. And so, yeah, it goes back to that admittance impedance strategy, right? And this is possibly even a modality that the wearer could even put them in. If there's a human in the loop and they know that there's someone else who is, I guess, teasing them in this case, stopping them from reaching something, if they would want to overpower, then you can use the impedance mode. If they would want to allow themselves to be guided, they might be able to switch their system into an admittance mode. So one easy way to answer that would just be maybe just offload that decision to the human who's in the loop. But maybe there's even a better response out there.
I think since the question doesn't specify, it also includes external robots just watching two people interacting for a task and trying to learn to do the task.
See.
But yeah, there is another question that asks, to help avoid people falling, isn't they feel that predicting 3 seconds in advance is a little complex, and to help with that, is it possible to use electrodes on specific muscles to activate those muscles in order to avoid falling? So I'm not sure if this is to actually activate the muscle from outside by sensing or just is it about sensing? So the question is it possible to use electrodes on specific muscles to activate those muscles in order to avoid falling by sensing them just before the action of falling, which seems to be easy? Uh, Feel free to
So,
interject that.
yeah. So, um, the approach of the sensor we had so far was more of a passive alert system, right? We're not controlling the person's body to try and directly avoid that. But you can imagine, to kind of set stone this in a little bit for me too, you can imagine the exoskeleton case, right? How does the input from a sensor that can predict gait instability inform possibly like an exoskeleton case? And maybe, an extension, a future extension to that would be directly, controlling someone's muscles to kind of help them react to a particular fall. I think that's a little bit out of my current space, but I think that's a really interesting idea, directly, controlling someone's muscles. But in the space of exoskeletons, right, you could totally imagine them using this information to help avoid the fall as well, if that's like an active component. If you're thinking about it from a sensing modality, absolutely. I think having, the ability to sense, particular muscle configurations might also be informative when it comes to predicting a fall. I imagine those models would be possibly more complex, but that's not a deterrent to using those as input modalities. One question, you have to think about too is, what does your end system look like? So I think from a research perspective, I think comparing what we have from external observations to possibly thinking about muscle sensing is a great space and dimension to look at. If you think about, actually giving this to a person to wear and walk around, what's the challenges for them correctly placing the EMG sensors on their body to actually get that information? That might be more cumbersome, which might reduce their desire to use the device as an end user. Um, you know, there's a whole space of solutions there, but that's an initial thought. One is you could imagine using a different type of wearable technology, and there are some companies, I won't name them, that are out there that actually have EMG sensors built into clothing itself. And so if you have that kind of coupled with your system, now you're having a different conversation about what kind of modality information you can input as well. So just as a general, thought, I think more information is always better than less information. So if that is available, I think it could be used in a helpful way.
Thank you so much, Professor Kennedy, for a fantastic talk. We couldn't get to all the questions, but the questions are still in Slido, and I'll make sure to pass them on after this. This is officially the end of the seminar. Thank you so much for joining us. Bye.